every time I come to IPAM, I learn something new. So, and this workshop is really great so far. So I think coarse-graining is really central to Emergence, and I hope I'll make this point during the talk. So before I start, I want to acknowledge my group. This is my group in Berlin, and we're still growing and hiring. So if you know any brilliant postdoc or somebody looking for a postdoc or PhD studies, let me know. And I want to start with this quote that all models are wrong, but some are useful. Everybody here makes models, so none of us is really making real things. I mean, we're all theories modelers, but we just need to pick the models that are more useful to predict something or to represent or to understand reality. I want to restart from where Mohammed ended this talk in the morning about AlphaFold, and we have seen how AlphaFold is predictive of the structure, so folded structure. But I would argue, from a physicist's point of view, what AlphaFold does predicts one point in an energy landscape. This is a very important point, presumably the minimum free energy in certain conditions, like, I don't know, conditions where the protein has been crystallized. But what we are interested in is the whole landscape. We want to understand, for practical reason, for application reason, we want to, as this is the same movie Frank showed this morning, we want to understand the dynamics, how the protein can change according to changes in the environmental condition and so on, mutation and so on, but also the dynamic itself is very important for the function. And so I think the overall landscape carries much more information than just one point. If we can understand your landscape, we can do a bunch of applications that right now are not, as Frank mentioned, there are challenges in all of them. Of course, this is very difficult because of the sampling problem, because in order to characterize the whole landscape, we need to being able to model a very large range of timescale. Frank showed a similar picture this morning, where there are different timescales, and historically people have been targeted different resolution, different timescale and different resolution, but it's very difficult to do the multi-scale thing and put everything together. And our idea is to try to find what is the optimal resolution where we can represent, at least from this time, from the nanosecond up to hopefully very long time scale, but preserving the relevant physics. So we hope that there is some emergent process that we can capture somehow without having to simulate the picosecond resolution. And so there are multiple questions here, and I'll address some of them. So when we talk about coarse-graining, we can talk about coarse-graining in different spaces. We can talk about, and this has been mentioned this morning, we can talk about coarse-graining in terms of reaction coordinate, like extracting a few parameters, clustering in a very high-dimensional space. If we have n atoms, and n can be like millions. We have a very high-dimensional space. This is the configurational space of the system. We can cluster in this space according to some. We can do a very strong dimensionality reduction and go into a space like a 2-dimension or so. And this is what was done in this movie here. In this movie here, there was a very strong dimensionality reduction, and the overall landscape was projected in this graph. So that we can do that, and this is a sort of coarse-graining in a dimensional space and coarse-graining in time. And we have done this, but what I want to talk about today is coarse-graining in structural space. That is coarse-graining in 3D. How can we partition the three-dimensional space? How we can partition atoms into some beads kind of things that represent with an effective Hamiltonian, and we can represent, hopefully, the real system. And this is similar to what people do in defining empirical force field, or even force field from machine learning force field. In that case, the coarse-grained electrons. Here, we want to take the next step and coarse-grain nuclei as well. On the first point, on coarse-graining in conformational space, we worked on that for many years, and this is a review not so new anymore, but on some of the work that us and others have done in this direction, on projecting high-dimensional systems in, like in this case, 2 reaction coordinates. But what I want to talk about today is coarse-graining in structural space. So coarse-graining is made of 2 steps. One is fixing the resolution. I don't know if I'll have time to talk about this. We have a recent paper came up 2 or 3 days ago in CS Central Science on how we think we can decide the optimal beads for in a coarse-graining, the first step. But when you have the resolution, then you have to decide in empirical in an energy function, an effective energy function, because it's the energy function that should represent the same thing as the fine-grained resolution, but with less degrees of freedom. So, and I'll show you that in principle you can write mathematical equation to define this energy function, but in practice people, because these mathematical equations are very difficult to solve, impossible to solve even numerically. So in practice, people have written empirical expression like this that we proposed in 2000. And so many years ago, and this is extremely simple, was called the ideal gas model of protein folding, very qualitative. And but many different expressions like this exist, and you can usually they represent local terms like bond, angles, dihedrals, and non-local terms that make the overall collective motion. In designing this energy function, you need to decide what you want to preserve, because you are doing a dimensionality reduction, so you cannot preserve everything. You may want to do a bottom-up, like really integrating out degrees of freedom, like a kind of renormalization approach. And this is, you want to preserve a fundamental description. You may want to start really from like the Schrödinger equation, then do a machine learning force field, and then go up to the coarse-graining force field. Or you can go top down. You can preserve global quantity like thermodynamic averages from experiment, for instance. Or there are other approaches like structural. We want to preserve some structural information, like in liquid. Usually, you want to preserve the radial distribution function and so on. I'll first talk about the bottom-up, then if I have time, I'll talk about the top-down, and our goal is, of course, to merge the 2 things. In the bottom-up approach, usually what we want to do, we want to represent the same thermodynamics of the fundamental description that is, in this case, what the force field, an atomistic force field gives you, with the coarse-grained force field. So in principle, you can integrate out, like you do in a normalization approach, you can integrate out the degrees of freedom and define an energy function that gives you the same thermodynamics. Basically, you marginalize the distribution. You take the marginal distribution, and that should be inverting that should give you the energy function. But this is impossible, and has been shown by Voth and co-worker that the same expression of the marginalization is equivalent to the minimization of this functional. So if U is the coarse-grained potential, if U can span the space of all function, all differentiable function, then the absolute minimum of this functional, where R is the average over the atomistic coordinate, gives you the potential U that is equivalent to the thermodynamic consistency. U reproduces the same free energy, same thermodynamics as the underlying atomistic potential. So this gives you a variational principle. What people have done have parameterized U with some analytical expression and with some parameter theta, and then minimize it in this space. But of course, this restricts the space of the functional space of U, and so you don't find really the real potential. You find an approximation. But so when we started to work with machine learning stuff, we thought this is exactly the problem machine learning is very good at, because you can significantly increase the expressivity of U by using a machine learning method like a neural network. And this is what we did back in 2019. This is what we called CGNet, and this is published a few years ago, so I don't want to spend too much time on this, but the idea is that we have something we can do with simply physical intuition, and we call it prior energy, and then everything else that we cannot get an analytical expression for, we put it in this free energy net, and we learn it from data. We approximate this ensemble average with data, with the atomistic simulation that are our reference, and we minimize this functional that becomes a function of the parameters of the neural network. There is something about this expression I want to mention, is that this F here is the instantaneous all-atom force, and R are the atomistic coordinate. There are two projection operators here. One is the projection, this is the coarse-grained mapping that projects the atomistic coordinate in the coarse-grained space. And one is the mapping of the forces into the coarse-grained space. And these projections is possible to show because basically you have because we do a dimensionality reduction, there is a null space that you can explore. So these two operators don't need to be the same. You have some freedom in picking the projection of the forces when you have defined the mapping. This fixes the resolution, gives you the coarse-grained coordinate as a function, usually as a linear function, or as like a linear combination of the atomistic coordinate, like the center of mass or just a slicing. But you have some freedom in picking these, and playing with these, we can do interesting things, as I'll show you later. This is our reference system. I'll show you all the results. We have many reference systems, but I'll show you all the results for the purpose of this talk on this system. This is signaling. That is a very small molecule. We picked it because it's a good test, because we can have a very good reference, because it's small enough you can do very long atomistic simulation in explicit solvent. It's a 10 residue protein, but even if it's only 10 residue, when you put it in explicit solvent, there's already several thousand degrees of freedom. And it's an interesting behavior because there's three minima in the landscape. So there is a folded state, but there is also an unfolded state and a misfolded state. So it's a already rich landscape, again, to underscore the fact that the folded state is not the whole story. It's a rich landscape, even if it's a 10 residue protein. So you can imagine how rich is the landscape of a protein that's like 300 residue long. And these are the three metastable states. So the goal is to reproduce a landscape with three metastable states, hopefully the same stability and the same barriers, with this much simpler model than this. And this is what we did back in 2019. This was really a proof of principle. So we have the prior energy is simply like the connectivity of the chain and some excluded volume. And we go to the resolution of only 1 carbon alpha per residue. So we go from several thousand degrees of freedom to 10 beads, so 30 degrees of freedom. And we can indeed reproduce the 3 minima. It's not matching exactly, but it can reproduce the 3 minima. And if we compare with what you can do without a neural network, like with the splines or 2 or 3 body only, you don't get anything. You get like a blob. You don't get 3 minima. So,
explicit solvent or
no, this is just 10 beads.
Okay.
Implicit solvent. Yeah, I'll talk about the solvent later.
The upper, that's like independent component analysis. What the TICA is? What?
TICA is that global coordinates, like PCA, nonlinear PCA.
Okay, but the top and the bottom, are they the same projection, or they're like just two?
They're this exactly same projection,
okay.
Same space.
Yeah.
Yeah, in order to compare apple with apples. Yeah. So we do this dimensionality reduction on the reference, and then we fix the coordinate and we project on the same space. Then later in 2020, we changed the architecture. We went a little bit more sophisticated. We used the work of Tachenko, Alex, and Klaus, which net that several advantages. The main advantage is that there's a transferable architecture. This is made of pieces that have the identity. So the parameters are shared among beads of the same kind. So if you change the sequence in principle, if you have enough examples, you can use the same parameters for a sequence you haven't seen. And this is the goal. This is a movie that was obtained with this, with the results of the training. We showed that we do a better job with this than before, and you see the molecule folds. And if you wait a little bit, it unfolds and refolds, and this is the free energy to explore. So it does what it should, but this takes it's very fast. You can do it on your laptop in a matter of maybe in hours. You see folding and folding transition, and it takes months to do the same things in the reference simulation. I mentioned about this fact that this projection here are not, they don't need to be the same. Usually it's always been taken to be the same, or just basically, yeah, let's say the same for slicing, when you take the mapping to be a slicing operator, just to pick one atom representing a residue, usually this is taken the same as this. But if you do this, there is a problem that you can decompose, no, sorry, let me go to, okay, I'm not going to the right order here. Yeah, here. You can decompose, this is what we showed back in 2019, you can decompose this loss function into 3 pieces. One piece, what we call the noise, is the baseline. So you have the bias, the variance as usual, but then you have the noise that is you cannot go below that. So this functional, the minimum of this functional is not 0. It's very large, actually, and it's maybe larger than the signal, the noise. And so this makes this learning problem extremely difficult. It's very data inefficient because you have this very large noise that you need to overcome. But this is because of this. This is only because of the dimensionality reduction. Basically, for each coarse-graining force, you have many possible. You have an ensemble of atomistic forces that are consistent with it, and you have to take an average over it, and that is the source of the noise. But you have this projection here, and because of the freedom in picking this projection, we played with it. This is in preparation for too long now. Hopefully, is converged now. I mean, we have the results. Just the people need to write the paper, as usual. And we showed that we can play with this operator here, and we can improve significantly the learning problem by reducing the noise, and we can get to much better. This is the reference, the same molecule as before. This is what you do if you take the same, and this is what you do, we get with optimize. We can get to very, almost, I would say, quantitative, I'll show you later, quantitative agreement between the reference and the learned potential. So we can really reproduce the thermodynamics at this point. But this part of playing with the noise was essential.
Quick question.
Yes.
Just to make sure I understand, so the idea here is that there's some underlying, the Coarsegraining is throwing away all the forces of the individual atoms. So there's always going to be some disagreement between your Coarsegrain and what was actually there. But why would picking a different atom to be the center atom, or I don't know what the variation here, like what would, what's the modified ER like here?
So the resolution is the same. You pick the same atom all of the time. When you project in this mathematical object here, in this functional, you need to project the force into the Coarsegraining space. But this projection, because you get these from the thermodynamic consistency, from writing from the marginal, you integrate the marginal integral by part, and you get an equivalence with this. But when you integrate by part, there is some freedom. There is a part that is zero, basically, that you can put in, and changes this projection operator. And that allows you to change the value of this noise. It's a statistical mechanics trick, basically.
Is it like a control variant, kind of, in the language of? I mean, it sounds like.
Yeah.
There's parts of it that I'm a little confused in that. I would think that if you wanted to minimize that you would kind of need them. I'm still trying to see how they can be not the same, but I can imagine that you might purposely bias it, but then end up winning a lot. But maybe
what you do in practice. So this is the atom that we pick to represent the old residue. This is the old residue. This is the atom, and this atom becomes a bead, everything else is. Instead of doing that, we pick a little bit of a contribution of all the atoms. So it's a different linear combination. Instead of just one, it's a linear combination of all the atoms in this mapping here. The mapping of the coordinates is the same.
Right.
And that reduces.
I mean, I see how you could choose them totally separately. I would just generally the thing that you go through to prove that the minimizer, the coarse grain, thing it minimizes what you want. I would think that if they're not the same, you're not necessarily going to. The thing that minimizes this is not necessarily the target.
Yeah. So this the noise doesn't have a deep meaning. In fact, if you minimize the mapping of the coordinates itself to minimize the noise, you get something completely meaningless. Basically, if you want to minimize the noise itself, if you want, like you say, I want a resolution that minimizes the noise, it puts all the atoms in one bead and then one apart. Like if you have two, it's completely meaningless, the noise. It's just the fact that you have an ensemble of atomistic configuration consistent with one coarse-grained configuration. And you have, it's called force matching, but basically for each coarse-grained force, you have many possible atomistic forces that are not consistent with each other. And that gives you the noise. But you can take different projections of these forces, basically. You can work in a different space. Yes.
So in some sense, the psi R acts on a very different space than psi F, right? Because one is on the actual configuration.
No, it's the same space, but you have a null space that you can play with.
But the forces, I think, live on the tangent space.
Yeah.
Right? So
Yeah.
it's actually a different space.
Yeah, you're right.
So I wonder if you have thought about formalizing what the actual conditions are
Yeah.
maybe for psi, right? Because in fact,
Yeah,
what you're writing here is some kind of equivariance on scale, right? It's basically you're saying, basically the map that acts in one part that gets, and the map that acts on these. So after the actual Coarse-graining, they have to be consistent, and that's exactly like an equivariance relation when you consider scale as a
because one is the
symmetry.
tangent space, as you said.
Yeah, and so, but you could also, argue that there might be other symmetries, like you want this map to be consistent under, let's say, rotations or under other actions of other groups in the space, and that you can give you a whole set of, I guess, relationships on what this psi needs to satisfy, and then you can pick in that space.
We have a very general relation on what this map needs to satisfy. Maybe we can show you the equation later. We can discuss it. And what we do, we want this. We pick among all possible linear map. Also, we have done some non-linear that minimize the noise. We don't put any other restriction. But maybe
is
we
it
can.
equivariant if I rotate everything?
Yeah, it's equivariant. So this was very important to get to the state of the art, but I skipped some part. So what I want to show you is that the neural network is very important here because there are very important multi-body terms that we don't know how to represent otherwise. We played a little bit with the symbolic regression, as we have seen this morning, but in this case, it's so multi-body that and very dimensional that if you have an idea how to do it, would be great. But we just decided it was too much at this point, and so we went completely into the neural network approach. So we showed this by doing a multi-body, many-body expansion. So we build architectures that are restricted to 2 bodies only, or 3 bodies only, and so on. And first we do the 2-body expansion, so basically just splines. And then we fix this, and we put the 3-body network in as a correction. And then we fix this, and then we put the 4-body network as a correction, and so on. So basically, it's a multi-body expansion. And we showed that the error decreases. I think this is the most important point, the KL divergence. This is what we want to match, what you would do if you put everything in the neural network. If you do 2-body only, the error is pretty large. If you add 3-body, it decreases, but not too much. 4-body, then it converges very, very slowly. And in this problem, this, of course, depends on the resolution. Here we go to the carbon alpha resolution for the same protein I showed you. You need to get up to 5 bodies. And then, and this means that at this point, we are stuck with neural network because I don't know how to write a 4 or 5-body potential that is expressive enough analytically to represent these potentials. And this is what you get with the multi-body expansion. So this is what you get with the neural network. This is back with the results of the first network, the 2019 network. This is the 2-body, don't get anything. 3-body, you start to get the 3 minima, but in order to be quantitative, you need to go to the 5 bodies. There was a question about the solvent. You can do the same thing as and to do the same coarse-graining, but decide to keep the resolution of the molecule and only coarse-grain away, basically integrate out the solvent degrees of freedom. So you do what is called in the field implicit solvent. And in this case, what you learn is the free energy of solvation. that is the energy of the protein with the water and the water by itself. The water by itself is not important. It's the energy of the protein with the water that is important. And we can do the same thing. It's just a modifiers net. And these are the results. So this is, again, the reference. The best performing network is this one that gets, again, I would say pretty quantitative. And it's really much better than state-of-the-art empirical implicit solvent method that is this GBSA thing here. And if you completely disregard the solvent, if you do vacuum simulation, you see that you don't get anything. And interestingly, this solvation model with the neural network can get the folding temperature quite well, while the implicit solvent model miss it by 100 Kelvin, because it's severely destabilizing the protein. So as I was showing earlier, this is the state of the art. This is where we are now. This is what we can match. So this is the reference, and this is where we are now. I would say this is quantitative now. These are the projection on the first reaction coordinate. So I would argue that we need to put error bars here, but I would argue that this is within the error bar, within the statistical error. So these are the free energy as a function of the first tick and the second tick. So these two coordinates here. Sorry. How do we get? How do we get here? There are a lot of pieces, moving pieces that we are putting together now. Is the mapping itself, the data set curation is super important. And yeah, so then the new architecture is super important. The physical constraints, these turned out to be very important too, not just the symmetries of the system and the equivariance and so on, but also the excluded volume was crucial. How do we design, we force the molecule to respect things we know, like the existence of bonds and the fact that two atoms cannot be in the same place. And because there are no examples in the reference about this, because it's forbidden. So there is no example, and then the network can do whatever. And then we need to, the asymptotics. The asymptotics, there is no example on the asymptotics because it is not visited. So we know the asymptotics from basic physics. So we need to make sure that all these things are enforced. And then the validation and the prediction, and eventually the comparison with experimental data. This is already discussed. Yeah, so the real challenge is to do it transferably. So what we really want to do, and looks like we're converging here, but it's a never-ending story. We want to learn on small peptides and small proteins, and then learn a universal force field, because, as I said, it's made of these pieces that in principle are transferable and are composable. So if we learn these parameters that are shared, then we can build any sequence and work with any sequence, also large sequences that are not possible in atomistic simulation. And I'll show you this as a teaser. We have much more interesting results now, but this is learning only on peptides, only on sequences that are 8 residues long in a split solvent. And then we try to simulate the usual molecule that is 10 residue long with a sequence that had never been seen before, and indeed find the correct landscape. This is an old picture, but anyway, we have better results now. But they are the 3 minima. This is what we wanted at this point. We are not going to reproduce it exactly, because this is a difference force field in practice. It's like, because it's extrapolating between different molecules. But we learned what was important, that is the three minima, the folded, misfolded, and unfolded state. And so this is a prediction of the network that is matching what we wanted. And as I said, there are many moving pieces that go into here, and they are also going to be important for the future. Frank mentioned this morning this force matching without forces. So the force matching that I discussed, that this variational principle allows us to enforce thermodynamic consistency without having to do the nasty integrals. There is another way to do it that is more direct, that is basically matching the distribution directly, because this is what we want, and it's called relative entropy. This requires, however, to basically write a KL divergence between the distribution of the reference and the distribution of the coarse grain, and you minimize it, but then requires to have the distribution of the coarse grain, so every time you change the parameter, you need to resimulate it. But when Frank did the Boltzmann distribution thing, it was clear that there are these density estimation methods that you don't need to resimulate. When you have an expression, especially a coarse-grained expression that there is no explicit water, so there is much more simple than an all-atom expression, you can estimate this density with these flows, and then you can combine the two things. This, as I mentioned, has this very large noise problem. This is the problem of the density estimation. We combine the two things, so without forces, we have the reference, we estimate the density for the coarse grain distribution, then we extract the force for the coarse grain distribution, then we match the coarse grain force. So this is matching the same thing, coarse grain force with coarse grain force, so there is no noise problem anymore. And so this is combining the two things thanks to the density estimation with machine learning. This is now published like yesterday, I guess, so I should change this. And this is really based on these normalizing flow methods that were discussed by Frank this morning. And we can do, with this, we can do much larger proteins, like Villain, BBA, TripCage. And these are the match potentials, and these are folding and unfolding events. So we can reproduce the free energy of all these proteins, and we can the cross here is the PDB structure, so we get the minimum in the right place, and also we match not just the structures but the mechanism. So if you look at the order of formation of different things in time, the reference and the folding events basically are on average are the same. Yes?
Can I ask a couple like naive questions maybe?
Yeah.
Could you go back a couple slides to, or maybe forward one, sorry. So this is like, that's actual time, so you have this coarse grain potential and then you evolve it forward with the coarse-grained, like you actually see dynamics. Right, so there's dynamics, and the other ones when you're showing the kind of free energy landscape,
that's
I don't know if you're
from the
getting
dynamics.
You get that through dynamics
From
also.
dynamics, yeah.
So I guess one of the questions I have is that when you're doing the dynamics on the coarse-grained thing, that variance in the noise from the atomistic forces is physical, right? I mean, it's actually. It is, those atoms are jiggling around, right? Mm-hmm. So like I guess what I could imagine that the timescales are so separate that all that noise averages to zero to like very high accuracy. And so then if you're wanting to evolve on a longer timescale for the coarse-grained thing, then you can basically ignore the fact that there's any noise.
I don't listen about the noise.
Like imagine you had infinite computer power and you evolve the atomistic system, and then you did the coarse-graining and you just watched what was happening.
No, the noise is still there.
What's that?
The noise I mentioned before, the coarse-graining noise is still there.
Yeah, exactly. So I guess what I'm wondering is like, to what extent that's important when you're simulating the coarse-grain system.
No, that's irrelevant.
It could just all average out to basically zero because the timescales are so separate.
these are different things. The coarse-grained noise is in the training. Once you have trained the model, that's gone.
I just mean, like, if I ran that in an atomic level system and I have everything that's going on and I follow what's going on with the coarse-grained thing,
Yeah.
From one time step to another of the atomistic picture, the forces are jiggling around.
Yeah.
And so then the question is, like, is that important for the dynamics, or is that totally irrelevant, right? Like, if the time scale of that jiggling around from the atomistic
Usually
stuff...
these are fast time scales.
So that's what I mean by the averaging.
In fact, if you average, for each coarse-grained configuration, if you average the atomistic configuration, that's exactly the coarse-grained potential you're looking for.
No, I understand, but I mean, and if those timescales are, like, very separate, then that's the right thing to do. But if the timescale of which things, it could be that the fluctuations that you see are actually important.
Then you cannot do coarse-grained, then you need to do some multi-resolution thing, because if the timescale, if you are averaging out fast vibration, and these are important for the function, then you cannot do it.
Yeah, so I was just wondering, so I guess part of my question is, like, to what degree, you look at, like, maybe there's no interest in it at all, but I could imagine that there's regimes where, like, understanding a little bit of that noise is maybe actually important. Like, the timescales are not necessarily as, like, so separated that it's completely negligible. And then in which case, like, I'm wondering if it would make any sense to actually try to track that noise and actually model that noise. And then maybe when you're doing the, like, Langevin dynamics on the coarse-grained system, you actually inject, like, purposely inject noise that comes from But maybe that's all totally irrelevant because, like, the scales are so widely separated.
So here we are looking at the folding or configurational changes, and the scale are really, really separated, like order of magnitude.
Okay. I don't know if
but for enzymes, this might be important for enzymes where you have very local changes, like a side chain flip or things like this. This may be important.
Actually, one follow-up on that. Can it be configuration dependent though? Because, even if on average this configuration has the following force, when it's in, when these side chains are in the proximity of something else, they may have a very different noise, very different.
Yeah, it's configuration dependent.
Right. And that could also affect the time scales, right, or not, right? Because you can get things where the side chains all up, they stop moving at the same time scale because of the configuration they're in.
The dynamics is, when we match the thermodynamics, we don't have any guarantee on the dynamics. So that's another thing we're exploring now, but the dynamics is a completely different beast.
Yeah, okay.
So we hope that at least on average, there is some rescaling we can do, but we don't know. Okay, so so this was for the bottom-up, what we have been doing and what we are doing now. I want to discuss the quantum part. So because we've been playing with these coarse-grained models for a while, was interesting that we talking with a collaborator in Cambridge, Venkat Kapil, was clear that this could be applied also to quantum system, in particular nuclear quantum effects. So whenever we design an effect in a force field, what we do, we average out, we take care of the electrons, but the nuclei are usually considered classical. And but there are situations where this is not the case, and the nuclei are quantum. Like hydrogen is very light, and there's sometimes quantum behavior, like you see here, like proton transfer or tunneling isotope effects. This is a classical hydrogen in this system. This is the quantum hydrogen, and you see if you use deuterium, you have more localization. And the quantum hydrogen is much more delocalized than the classical hydrogen. This effect may be important at a very low temperature, things like this. So there is a quantum classical isomorphism that, for instance, is extremely well explained in Mark book that I give to all my students to understand this part. So Feynman, you may be familiar with Feynman path integral. And basically, instead of considering the solution of the Schrödinger equation giving you the wave function, you can consider the classical equivalent, but instead of one particle, an infinite number of particles, and then you take all the trajectories, and that gives you the probability distribution, basically. And there is an isomorphism. If you have not just one particle, but, for instance, a molecule, then there are rules on how to design the replicas that are all in principle, in order to be exact, there need to be an infinite number of replicas. They are coupled with each other. So in practice, what you get is a system, a classical system of many, many particles that if you can find the classical distribution gives you the same result. If you do averages with that, you do get the same results as for the quantum system. So the price you pay, you go classical, but the price you pay is that you have many, many copies of the system, so it's very expensive. And this is the quantum, the Feynman path integral formulation is called, yeah. And but when we thought, here you have, what you get is a polymer, basically is a ring polymer, because all these replicas are coupled together by springs. And so we are good in coarse-graining polymers, so we can do the same thing here. We can do the reference simulation are the classical path integral simulation. And then we coarse-grain it back to 1 bit. So if everything works, we get one classical bit that has the same, gives you the same result of the quantum bit. So instead of paying the price of the multitude of classical bits, you renormalize it back to 1. But this 1 has a different energy function that incorporates the quantum effects. And it works. So the idea is, can we coarse-grain the ring polymer back to a centroid? And this works. We call it PIGS. Yeah, so this path integral coarse-grain simulation was published last year.
So can I ask a question about that?
Sure.
So this is finite temperature, right? But because it goes in a circle, the path integral formulation is between two separate points, but this is like on a...
No, it's because you have a boundary condition.
Right, so it's in imaginary time or something like that.
Yeah, yeah.
Okay, and how can I read out the temperature from this formulation?
So the temperature enters because when you do averages, like you do with this Hamiltonian, you do statistical averages, so there is a temperature Boltzmann factor.
Okay, so in front
it's
of
a statistical,
the
yeah.
H, okay.
Yeah, H is the Hamiltonian, doesn't have a temperature.
Okay.
It does. It does there. It does in omega p.
Oh,
There is a T in
right,
the
yes.
kinetic energy part, right? You know,
P is beta. There is a beta
Beta,
here. Yeah, there is a beta. The temperature is in the coupling of yeah. So basically, if you lower the temperature, becomes more and more quantum. The coupling becomes.
I thought it was related to the length of the basically.
Also, that P is the number of replicas. It goes to infinity in the exact case, and as you lower the temperature, it becomes more and more quantum. So you become more and more replicas to reproduce the system. At zero temperature, you cannot do it. And I'll show you some results here. So we did the dynamical counterpart. So there are some differences with this static, but for any purposes, this is the idea. We first did the OH bond because it can be reproduced, it can be modeled with the Morse potential that is analytically soluble. And this is the reference. So this is the spectrum. of the quantum system, and this is what we get with our PIGS method at different temperatures, and we reproduce very well. Here, the peak is arbitrary unit. What you want to match is the position of this peak in the spectrum, not the height. And we get very good agreement. These are competitive methods that have this blue shift with the temperature that is not what, you shouldn't have this blue shift. The peak for this system is not temperature dependent. And the reason why we don't have this blue shift, this is a bit technical, but is what we call the temperature elevation approximation. The idea is that when we match this energy function here, when we simulate this energy function here, we learn an effective potential. If the system is, because then we do Boltzmann averages, if the difference in energy between the ground state and the excited state is very, very large, below a certain temperature you populate only the ground state, and so you care only about the effective free energy of the ground state. And the effective free energy of the ground state is not depending on the temperature. So you learn that at a given temperature, and then you scale the temperature trivially. This is what is this temperature elevation, and you get rid of these effects. We can discuss it later, but we will get rid of these blue shifts. But this works also for more complex molecules like water. This is one water molecule. Our results are in red here at different temperature, and the reference is the DVR, that is an accurate quantum reference calculation, and you see it matches very well the peaks. And because we don't have this temperature problem, we can go to cryogenic temperature. That is where the experimental data are available, and we can match the position of the peaks, the experimental peaks. And we can also do bulk water, also go to cryogenic temperature, and we also see here our results are in red, and the reference is in green, and we match the positions of the peaks. No, I think the reference is in black. Yeah, the reference is in black. Okay, so this is what we are. Now we are trying to do much more complex systems where we can really make predictions of something we don't know, like more interesting molecules when you have proton transfer. Maybe, hopefully, we can go to enzymes or things like this.
So how many beads did you coarse grain the ring polymer?
40.
40?
No, 64. 64. Because we did it at, let me see, we did it at 300 Kelvin. So this is the trick, that you do it at 300 Kelvin so that you don't need too many beads, but you learn an effective energy, the ground state free energy, that is not depending on the temperature. And then you use that free energy, just changing the Boltzmann factor, and you can lower the temperature to cryogenic temperature.
And so big advantage is that you can make much longer time steps.
Yeah.
Coarse-grained representation, you need super tiny time steps in this half integral formulation, like 0.1 femto per second, something like that.
Yeah.
So in the ratios of like Boltzmann factors, when you make those temperature changes that big, they don't explode and you get nonsense?
No.
It's sort of, I don't know at what point that starts to not work. Like at least in our lattice QCD things that we do, we try to do those changes in temperature, but we have configurations where, it's like pretty small changes in temperatures before it all kind of.
So as long as it stays in the ground state, you don't get surprises. When you go to temperature where you start to excited states, it becomes much more complicated. But if you stay in the ground state,
It's fine.
it's fine.
I can see.
Yeah.
They should probably wrap up soon.
Yeah, okay, sorry. So I can, then I'll skip all the rest. So here I want to tell you something about the top-down, but the essence of the story is that instead of trying to estimate the amount of multi-body terms bottom-up, we can do it top-down by designing more and more complicated energy functions and trying to match experimental observation and see what you need to match reality. What we have so far, I mean, the methods are not that important, but with the observables we match is free energy differences upon mutation. So stability differences upon mutation using perturbation theory, but it doesn't matter. But the message here is that if you have, so if you want to represent the effect of solvent, so if you want, for instance, to represent the free energy difference upon mutation of residues that are exposed to solvent, then there is where the multi-body effects are essential. This is not surprising, perhaps. So if you change from two-body to many-body, you get a very different result. And at this point, we have done it with functional forms, but hopefully in the future we can do it with neural network. So in the future, we would like to combine all of this. And thank you very much for your attention.